So welcome back to System Software. So the first half we looked at system tools, using them and writing. We wrote a couple of system tools. We still have the proc project out. Midterm's over. It's still being graded. So if you do see a score, it's probably not your final score. So the GTA is currently going through the long answer question, and then there was a multiple choice question that I messed up the answer for. The directory and file names one. So that's not your final grade. It's probably your minimum grade. And also, if you are worried about like short answer or other questions, come to office hours. Also give partial credit if you're worried about any of your answers. Attendance, if you took a paper exam or an essay, or if you took an SAS exam, you may not have your attendance updated yet. We're still getting to that. If you took a paper exam at all, SAS or here, we haven't graded those yet. So just give us a little time. Limited staff, limited people, and hundreds of you. So we're still grading the exams. But feel free to come to office hours if you want to go over your exam early, you want to look for partial credit or see what you got wrong. Feel free to come to office hours anytime. Questions on the exam, questions on, yeah. No, it's partial credit. Yeah, for the long answer ones, there's definitely partial credit. Also for the short answer ones, there may be partial credit if you come. We'll look at them as well. But yeah, there's definitely partial credit for the long answer one. And it's only worth 1 point on the question, but it's long answer. Yeah.
How many points were like the long answers were compared to like the 8-point scale?
The 8-point scale. So it was. They were all weighted equally. So 20 questions, 20 points on the exam. I used to make it so that 1 point was 1 percentage point for the exam, but that's getting too hard to do. It'll be 20 or 8 points divided into 20. So each question was worth 0.4% of your whole grade. I guess you could look at it that way. But yeah, they're all equally weighted. So even the hardest one, the long answer one, is equal weight as the multiple choice. Other questions on the exam? I know you're excited to get your grades back, or maybe worried about that partial grade in web courses, but it's not the final grade yet. Probably take another week or so to get all the grades out. Other questions on the class? Shells, the homework assignment? So yeah, FS project should be fully graded. There was some snafu with some of the feedback. So if you didn't get a feedback report, let us know on EdSTEM. If you want to resubmit your project, remember you can always resubmit your project with just a single one-time 1-point penalty, and you can still do the bonus exercise, so you can still get 9 out of 8 on the FS project. So just when you push it, just let us know on EdSTEM. I think there's a lot of regrade requests, so Sanan will just do a mass regrade periodically, but let us know on EdSTEM about any regrades. And then just as a reminder, the proc project will be due, what's that, 11, 12, in 10 plus 2 days, 12 days. What's that? Yeah, that sounds right. Yeah. Yeah, you'll still get extra points. So if you resubmit and you get the bonus questions, that's 10 points minus 1 point late penalty. So you'll still get 9 out of 8. So with the bonus, you can still get over 100% on a late submission project. So that's the grading scheme, the kind of forgiveness grading scheme. So you can still try to get your project working. Yeah. I'm sorry, say again? Sorry, say it one more time. Yeah. It might have been you missed some other questions that were not bonus questions. So take a look at the feedback report if it's there for you, and it'll show you which test cases you got right or wrong. But feel free to come to office hours, and I can go over the report with you and help you with any problems with the test. Yeah. So the feedback report will show you exactly which test cases you got right or wrong. Now remember, only half the test cases are going to be released. We never release the bonus test cases or the other half. We describe them to you. But I'm happy to go over them in office hours in more detail. Other questions on projects, exams, content of the first half? And there's no homework to go over, so questions? What questions do you have? Anything else? All right, let's do attendance. So the next half of our class is going to be about compiler writing. It's not going to be a full compiler. We're going to look at the back end of the compiler, the part that interacts with the rest of your system software. To give you some context for that, today I'm going to just give you a walkthrough of how your source code actually becomes a process, actually becomes a running program on your machine. And you may be surprised how much goes into actually taking that source code and making it run on your machine. So not only the compiler, but there's a whole bunch of other parts of this system software that come together that actually make that hello world program, even something simple like that, actually run on a physical machine. All right, so if you remember one of the earlier questions I asked you, does C code get executed by the processor? Who says yes? Who says no? It doesn't get executed, right? What gets executed by the processor? Yeah, machine code. Machine code gets executed. And if you want to have multi-process, you want to have multiple processes running at the same time, you need more machinery than just machine code. You need a way to load that machine code into memory. You need a way to do time slicing and process management. You also need to, by the way, boot your machine and all that. But okay, so here's an overall diagram of all the steps that go into turning your source code into machine code and actually getting run. And I'm going to illustrate most of these steps, except the running program, which we saw with exec. That's basically exec. Okay, so we start with your C code, and we end with a running program. We saw that in the first half. That's exec. Exec is the loader. So the first step is the C preprocessor, and this resolves your header files, macros, those pound includes that you have at the top. That's not actually C code proper. That's the preprocessor language, and we can look at that a little more closely if there's time. So then we get this intermediate file, this pure C file after preprocessing. And this is where the compiler comes in. So the compiler will take that C code and it'll translate it into machine code, assembly. But if you remember, assembly is, so what is assembly code? What's the assembly code, and what's the difference between assembly and machine code? And that sounds like a loud storm. What's the difference between machine code and assembly code?
Isn't assembly code where, like this,
Yeah, what are you going to say? Yeah.
like, it's the most basic form. It's like you're actually writing the if statements and counting.
That's close, although I would say the machine code is the more basic form. Yeah, go ahead.
Assembly is like CPU instructions, and machine code is like the binary, like that.
Yeah, I mean, it's getting at the right thing. So the difference is, like, machine code is what the actual processor accepts. It's usually encoded in binary. And assembly code is, just like in C, assembly code is written in ASCII. It's written in, like, human readable text. So as a shorthand, we might say assembly code for the machine code. But it's just text, just like C code is just text. And the text has no meaning to the processor. The processor, you have to put the right opcodes and encode it in binary format. So even though if you have assembly code, yeah, go ahead.
So is that why writing in compiled languages can be slightly more risky than uncompiled, because the machine code will not stop you from deleting important things, for example?
Oh, okay, that's an interesting subtle question. So is it why compiled languages are sort of less safe to write in? That is sort of, I guess you could say in a sense that's true, although, so yeah, I'm not going to talk too much about scripted languages here, scripting languages. So these are not compiled languages that are run. Those are basically interpreted by a software machine, you can imagine. But yeah, compiled languages like C don't do a lot of checking of your code before you compile it. So yeah, you have a lot of freedom to mess things up, like try to dereference 0, null pointer dereferences, and other things that cause seg faults or hardware traps. So in some sense, yes, but you can also encounter those errors in runtime languages as well, but they're just not running on the bare metal of the machine. In modern languages like Rust and Go, check for memory safety at compile time. So in some sense, that's true for C and assembly, You have freedom to like do any operations you want on the hardware, even if they lead to failures. So in some sense, that's kind of true, but there are more subtle reasons for that. But for us, the machine code, it's just binary. So assembly you can think of as like the lowest level thing you can write in human text. So assembly code is just human readable text that has mnemonics for the opcodes instead of the actual binary encodings of the opcodes. And it's the assembler that translates that human readable machine code or the human readable sequence of machine instructions and turns it into actual machine code, the binary encoding that the processor will take. And the output of the assembly is called an object file. And an object file is that binary machine code in a specific file format that'll allow it to be turned into an executable file. Once we have machine code files, the linker is what combines them into an executable file. It links multiple object files into one object file along with any library code, like what you use for printf or the other functions that you call that you haven't defined yet. And then finally, once we have an executable file that has machine code in it in the right format, the operating system's loader, which gets called by execve, which you used already, this is what takes that machine code, loads it into memory, and then kicks off the processor to actually start executing that code. So questions overall about the process. So as you can see, just writing a Hello World application involves a huge amount of software, huge amount of system software to actually get this running on your physical machine. So it's easy to take for granted Hello World, but a lot of work has gone into developing this infrastructure. And for basically any computing device today, except maybe the lowest level microcontrollers, has a tool chain like this to get code running on your machine. And even if you have something like Python or a runtime language, those are eventually have to be written in some language that's going to be compiled to the machine code. So the Python interpreter itself, the most popular one is written in C, that interpreter. So that Python program is a C program that is running and compiled along this tool chain. All right, questions? Questions about these sort of high-level steps so far? I think you've probably learned about some of these, right? So in computer organization, did you learn about assembly and machine code? I think so, right? Okay. Did you learn about linkers in computer organization? No? Okay. All right, so I'm going to actually show you running each of these tools. I'm going to show you concretely what each of these steps looks like. I'm going to bring up my guide here. Yeah, I'm going to put this on the other page, give myself more space. Yeah, that's too small. Okay, so let's start with just a simple Hello World program. And so we can do that with cat, if you remember. So here's my Hello World program in hello.c. Let me remove everything in here. Should be the same. Okay, written a little bit differently, but here's my Hello World program. It main, it just prints Hello World. Okay, so let's look at the first step, preprocessing. So just to give you a sense of what the preprocessor does, here's how we run it. So I should just say that GCC actually runs most of these steps for you. So I put GCC, the compiler, here, but all of these steps here, except the loader, actually get run by GCC. GCC will call out to these tools for you, but they are separate tools. So GCC, we can run the preprocessor with this -e flag. Don't worry about remembering like these flags. I just want to show you what the output of all these look like. So we're going to preprocess hello.c, and the standard file extension for the preprocessed C file is called hello.i. There, it's been preprocessed. And now we can see, if we look inside, let me just let me show you in Emacs. So there's the C program. So here is hello.i. It is several hundred lines of code. And you can see there's just a huge number of declarations. Where does all that come from? Well, here's a line from our original code. All this extra code above our main, what was there before? Headers, our include standard IO file. So all include does, and all the preprocessor does, is literally copy that code from that C file. So that's here in user include standard IO. That's this file here. It literally just copies this file, effectively copies this code into my hello.c file. Does other stuff like macros and expansion, but that's effectively what it does. And you can see that there are lots of other nested include files, so we end up with literally hundreds of lines of extra declarations. So that's why when you type printf, when you want that function, that printf function, your compiler doesn't complain. It knows about that function because this header file declared it. If I had taken this out, modern compilers will still compile it, but it'll give you this warning. So that's why it gives you this warning. It detects that you're calling a function that you haven't defined, and it has a database of which functions and which headers they're stored in. But okay. All right, so that's pre-processing. And that's just the very first step. So now we have this hello.i file, which contains all the header inclusion, all the macros expanded, plus the code that we wrote. Now that we have that, the next step is actually compiling the code into assembly. So the flag for that with GCC is -S. So I can take that intermediate file, that preprocessed file, and produce a .s file. That's the extension, common extension for assembly files. And maybe this will look a little familiar, maybe not. But you can see there's instructions like move, call, you would see add, subtract. Hopefully, I know you probably learned RISC, I think, or MIPS in computer organization, but there's instructions like load and move in MIPS, right? So this is the assembly for the Intel architecture. My machine is Intel, uses is Intel. This is the assembly code that gets produced. And we'll learn a little bit more about assembly code when we generate our own compiler, yeah.
Does the compiler differentiate between the AMD versus Intel versions, or is that actually the hardware itself?
Oh, that's a good question. So since the compiler, once the compiler's job is to produce machine code that will run on our architecture. So if we want to target an Intel architecture, our compiler needs to generate those Intel instructions. If we want to generate ARM or MIPS or some other architecture, we need a different compiler, or we at least need a different part of the compiler. The part that's actually writing out the assembly code, we need different code to do that. So effectively, each architecture and each front-end language has a different compiler. You have to write a different piece of software to do that translation. So GCC supports lots of different languages, so you can do what's called cross-compilation, where if you want to compile for ARM, but you're on an x86 machine, you just download the compilers for the ARM architecture, and then compile your C code to ARM or whatever device you want to have, if that makes sense. So yeah, you have to write the compiler specifically for that problem, for the problem of generating x86 versus ARM. And yeah, it's a different compiler, basically. Modern compilers are engineered so that they're sort of modularized, so they can target multiple different back-end architectures, but it's new code. the compiler writer has to write new code. Yeah.
So then if, per se, you had a CPU that didn't have a compiler written for it, if you tried to then run the compiler or run the machine code, would it just crash the whole system?
If you try to run the machine, well, yeah, so we haven't even gotten machine code yet. We're at assembly. So if we turn this assembly into x86 machine code and tried to run it on a different architecture, yeah, that architecture, it would not work as expected because the encodings for different opcodes, so hopefully you learned this in computer organization. If you took MIPS opcode encodings and tried to use an x86 encoding, it would not be meaningful in that architecture. So it may accidentally run other opcodes for that architecture, but MIPS, doesn't have many opcodes that x86 has. x86 is CISC. It has lots of different opcodes compared to MIPS. And so if you try to give it an encoding for an instruction that doesn't exist on MIPS, MIPS has got to try to interpret that as a MIPS instruction. So this is kind of like when we talked about ASCII versus numbers. So the ASCII encoding uses, say, 48 or something for the glyph 0. So if you had a different encoding for symbols like EBCDIC or ANSI or UTF-8 or something, a different encoding, that glyph, that symbol for 0, would have a different number behind it. So if you tried to interpret it under a different encoding, you'd get different symbols, like different languages. You can use different languages to refer to the same thing, but you might have accidental puns in different languages, for instance, or false cognates in different languages. So I don't know if I hope that answers your question, but yeah, the machine code is specific to the machine, and this is really the story of why compilers, part of the reasons why compilers exist, because we can write C code and it's more or less portable. We can write the same C code and then compile it for different architectures. So the Linux kernel, for instance, it's written in C, although it has, maybe that's a bad example. So take an application like LS, the program LS. It's written in C, basically portable C. So you can recompile that for ARM, you can recompile it for MIPS, you can recompile it for whatever you have a compiler for. You can recompile it to a different architecture and have it run on that hardware. And we'll actually write our own compiler backend in this class, and I'll talk a little bit more about actually generating code. So it's literally, I'm going to get to this more next time, but you literally write a C program, and that C program prints out assembly code. You literally just printf assembly code, and that's kind of the crux of compilation. You generate code from your program. And that's how this assembly code here, that's what GCC did. It took our C code, and it generated assembly code that corresponds to the behavior of that C code. So if I write a return statement, I need to generate assembly code that's equivalent to a return statement. If I write arithmetic, like using an ASCII plus symbol, that plus symbol has no meaning to the x86 architecture. That asterisk has no meaning to the x86 architecture. I need to translate that into an add command or a multiply opcode for the x86 architecture. That sort of makes sense? All right, so this is the assembly code output from our Hello World program. There's a lot of other extra stuff in here that I'm not going to go over, and also I don't know about entirely. And we'll cover assembly in a couple weeks when we actually get into our compiler. But you can see here's our call to printf. Here the compiler has substituted putS, which is just a different call. It's put string. So if you use printf without any other arguments, it's the compiler replaces it with put string, or actually the C code the compiler effectively replaces this with putS. PutS is just another library call. So this is just writing a string out to some file. But yeah, there's our call. This is basically our return value. But anyway, we'll get into actual assembly later. I think you all have some experience with a little bit of assembly. But yeah, this is what the compiler does. It takes C code and translates it, just like any language translator translates it into assembly code for a specific architecture. All right, questions so far? Other questions? All right, so there's pre-processing, compilation. Now we have this text file. This is still ASCII text. So if I were to show you a hex dump of this assembly file, these binary values displayed in hex here, these correspond to ASCII code. So if there's, say, I can't see where call is, but call, there is a call opcode in x86, but it does not correspond to whatever this hex code is. This is the hex code for ASCII, the ASCII representation of the word call. But in x86, that opcode is an entirely different number. It is not this number. And so to turn this assembly code, which is just ASCII text, into the actual binary encoding of what the processor supports, that's what the assembler does. Part of what the assembler, it also does other stuff, but one of the main thing it does is it turn this assembly code into machine code. So let's take a look at that. So the assembler in the kind of Unix programming environment is called AS for assembler. And so we take in the .s file and produce an object file. Now at this point, the object file is no longer ASCII code, or at least mostly not ASCII code. And if I try to view it, I actually get a warning from the less tool. Most of the characters are not printable characters. They're not hexadecimal printable characters. So if I do hex dump, which prints out the hex encoding of this binary code here, you can see most of the characters are dot on the right, which means non-printable ASCII code. There's very little ASCII in here. There's some, so my hello world string, that's stored in there. That hello world string is actually stored in ASCII in there because that's the representation that printf uses. But the rest of this stuff, no more assembly, no more C code. So we need other tools to be able to view what this contents is. I mean, here's our hex code. We can disassemble this. We can actually disassemble this code with a tool called object dump. So obj means object dump. This is how you can work with these object file formats. And we can take this object file and we'll actually disassemble it. It'll take the machine code and try to figure out what the assembly code originally looked like. So here's our disassembled program. You can see this is the hex codes of our actual operation. So you can see that the call was, I guess, this, EA. I don't know the machine code for assembly, but these are the hex encodings of these opcodes over here. And I do not know Intel encoding well enough, but this is what the machine code looks like in hex, and this is the corresponding assembly code that was disassembled from it. Questions on that? All right, so now we're down to machine code. How do we get this to be runnable? So object dump will also show us what's called the linker table. So the linker table tells us what functions are defined in this object program. So what functions we defined in our program. So we defined a main method in this program, right? And we called putS. Remember, printf was turned into putS, as put string. So putS here, this is telling us that that function is not defined. So we didn't write this code, right? We included the header file for it. But the header file is just declarations. It doesn't have the actual code. So in order to combine the actual implementation of putS with our program, this is where the linker comes in. So this is what library code is. Printf, all those system calls, these aren't defined in your own program. Instead, somebody else wrote them for you, and we want to use them in our program. So how do we do that? This is what the linker does. The linker will take code that other people wrote, and it'll combine it with your code, and also combine it with the code we need to make it an executable program. So let's take a look at that instruction. So this is not something I can write off the top of my head because there's a whole bunch of library code that needs to be combined here. So this is getting into low-level details of the system that are also beyond me, but this is basically the C runtime. This is what calls the main method. This is the C library, which has things like printf in it. And so this is the dynamic linker. So I'll talk about it in a second, but effectively this is providing access from your code to library code like putS. All right, so I've linked my program. Now if I do object dump, and I disassemble hello, so I produce this program called hello, you'll see here's my main method that was here before. But there's a whole bunch of other code in here. So this code is for helping us find the other functions to call. But you can see that we have our own code in here, and then we have this other code that was brought in by the linker. And now we can run this program. If I tried to run hello dot, oh, well, it's not executable, but even if I made it executable, it's not in the right format. It doesn't, it won't be, the loader won't be able to run this program. But if I run the hello program, now it'll work. So my code that I wrote that calls printf or putS to print the string, now that has a definition of that function in my program. And so this, when I actually used bash, what got called when what syscall is made when I run, /hello? What syscalls get used? What does bash use when I run /hello? Say again? Exec, yeah, exactly, exec. So bash calls exec, and that's the loader. That's the part of the system that will take this file on disk, this binary code, and load it into memory and start actually running it on the processor. So that's the final step. This is the whole tool chain that gets us from source code to an actual running program. And we can see that the linker has, main is still here, that's what we defined, but you can see putS. Okay, this is the dynamic linker. Let me show you the static linker so I can convince you that the linker is actually including our definition of putS in here. So our hello program now has a definition of putS, and it has our definition of main in the same program. If we disassemble it, there's going to be a lot of stuff in here. But you can see that something related to putS, the code for it is actually in our file at this point. When before in our .o file, our object file, there was only a definition of main. But in our linked file, we've got main. This is our definition of main, and we also have putS with lots of other stuff that's in putS. So all the code that's needed to actually call printf is now combined in our application. And that's what allows it to actually run and print out hello world when it gets run. Questions on this? Questions on this process? Yeah?
So .o will always only be the main?
Say again?
.o will always only be the main?
That's a good question. So not necessarily. So if that's actually a good segue into the next section. Not necessarily. So you can define any number of functions you want in your code. It doesn't have to be main. So the C runtime, the C language infrastructure expects you to have a function called main. So if you've ever seen this error where, let's take our let's take another implementation of hello world, but instead we put it in a function called hello. So what's going to happen when I try to compile and run this program? Or what do you think? Has anyone ever tried to do this or encountered this error? Maybe not. All right. So I'm going to get a complaint here that there's an undefined reference to main. This error comes from the linker because the C runtime, that is the infrastructure for the C language, expects that you have a function called main. That function is mandatory. It has to be defined in order for you to actually execute your program. But I can take this program and I can so if I do -C, it'll just compile without linking. So I could go through the whole tool chain again, but I'm going to avoid going through the whole tool chain. But I can just compile this program into a .o file. So here's my .o file for hello2. if we look at the contents of this file, you'll see that we've got this function called hello. There's no main function in here. There's no main function in hello, right? But the linker, linking with the C language infrastructure, expects there to be a definition of the function main because it has code that calls main. So what the C runtime does is it sets up like the argument and the environment, and then it calls main. And if that main function isn't defined, you get a linker error. That's why you get this error when we try to compile hello 2. So this error happens here. So there's no problem with the program here. There's no problem with just defining a function in a C program and compiling it even to machine code. The problem comes when the C infrastructure requires a main function in order to create an executable program, because that's the expected entry point to your program. That's the first function that gets run. And notice that at this point, even if I have a main function, like in my original program, this was my original object file, I just have a definition of the program. There's nothing special about main until I want to turn it into a C executable. You can define whatever functions you like. The C executable expects a function called main in order to, as the starting point for your program. But that's just, that has nothing to do with the compiler itself. The compiler doesn't care about that requirement. It's only the linker, when you go to link with the C infrastructure, that calls main. That's the only time it matters. All right, so yeah, that's a good question. You can define any functions you want here. All right, other questions about this whole tool chain? Yeah.
Can you ignore one Dado?
No, you can have many Dado files, yeah.
So does it branch off to get some of the, like every Dado will have its own executable file into the running program?
There'll only be one executable file and multiple Dado files. So this is actually called separate compilation. I showed it a little bit at the beginning. So let me actually walk through this since getting good questions on this. So let me make an example of separate compilation. I touched on this briefly when I talked about makefiles, but let's do an entirely other example. Yeah, I guess this example should work. Let's take okay, we'll just take two programs. And I'm just making a new example. I don't remember these examples well enough. All right, so I'm just going to make a function f here. It's not really meaningful. I'm just going to make it return. Let's have it take a value and, I don't know, add 2 to it. Doesn't really matter what it does. So I got this function definition here. And I'm going to compile it. Compile successfully. I didn't try to link it yet. So if I try to just call GCC by default on f.c, it'll complain I don't have a main method. But that's because GCC is trying to compile and link the program. So I'm just going to compile it with the FC. And I get this f.o. So in here, f.o defines this function called f. And I could make a function called, let's call it my program, myprog.c. So the question was about separate compilation. So if I've got this function f, and I compile it, in my linker table, it says and from object dump, it tells me that I have one function named f here. I can define another C file that defines one function called main. Remember, the function main has no meaning to the compiler itself. It just translates whatever functions you have defined in your program. And we can even define other multiple functions in the same program. So let's say this just calls f. Let's leave this aside for now. So yeah, let's call g. So this just calls the function f with the number 4, and all main does is it prints out what the result of calling g is. All right, so here are my two files. So now, like, the easy way to do this is you just put both C files on the command line, which maybe some of you have learned. Oops. So it gives me a little complaint, but it should still run. And yeah, I get 6, so it's calling f. So let me just walk through the code and make sure I'm clear on the code. So this is main. Main calls g. G calls f, passing 4. And then f takes 4, whatever the value is of x, adds 2 to it and returns it. Then g returns that value to main, main prints it out. Questions on the behavior of this code? So it's just multiple function calls. And if I just compile, tell GCC both these C files, it'll kind of do the right thing for me. But what's really happening under the hood is each one of these programs is being compiled separately. So I'm compiling f.c, and I'm compiling my prog.c. And here you see it's complaining that it doesn't know what the function f is. Yeah?
So when my prog, my prog is the bottom one, right?
My prog is the top one here, this
So
one.
when the bottom, or f.c,
Yeah.
when that reaches the linker, how come it's not giving like an error?
So let me walk you through what happens when what GCC does here. So it compiles each of these individually. So it compiles GCC-C f.c, GCC-C myprog.c, and it creates these two separate compilation units. So it does these steps all the way up to the object file for both of them, but doesn't call the linker. It just creates the machine code for each of these. If we look inside the function tables, the linker tables for both of these compiled programs, here we've got a function, or a program that defines the function f, and in my prog.o, we have a program that defines main, it defines g, but it doesn't have a definition, so it says undefined, doesn't have a definition for f, and it doesn't have a definition for printf. So it has the code for main, but it has calls to f and printf. Whereas f has f, the function f, but it has no definition of main or anything else. And also notice that when you compile my prog, it complains about f not being there. That's the same thing we see when we don't include the header file. If we didn't include the header file, the compiler is just trying to compile this program by itself, and it sees that there are calls to two functions, printf and f. And these calls aren't defined anywhere. It doesn't know what the parameters are or the return values to these. So that's why, what standard I/O does, it really is just a bunch of function declarations. So in order to tell the compiler what the type of f is, we can just do a declaration. So this is just declaring f to be a function that we can call, but we don't actually provide the implementation. So there's no implementation here. There's no curly braces. The implementation is in a different program. So here we're defining a program that calls a function, but that function doesn't have to be defined in order to compile this program, because it just calls whatever f is. It doesn't have to know what f is. It just has code in here, so if we dumped myprog, tried to disassemble it, or looked at the assembly code, we'd see in here, well, let me compile it to assembly, because the disassembled one is less easy to look at. So the assembly version of this program calls G in main, and then G calls F. So you can see F being called here. So the call to F doesn't need, the opcode for calling F doesn't need the implementation of F to actually write that program, to write that assembly code. But when we run this program, yeah, we need to have some address for F for it to call. But we don't need it when we actually compile the program. We don't need to know where F is in order to write an assembly instruction that says call F. So call is basically just a branch to F. Does that sort of make sense? So you don't need the implementation of F to write code that calls a function F. So that's why we can write these, we can put these functions in different files. It's only when we go to try to link these programs. So if I were to try to just compile myprog by itself, it's going to complain that there's no implementation of F. Just like if we had no main, it would complain there's no implementation of main. There's no implementation of F here. So what's happening diagrammatically is we've got these two C programs, myprog.c and f.c, and we compile and translate them, so GCC and assemble. We compile them separately to object files. The object files just contain the machine code translation of that C file. And even though myprog calls a function F, we can still compile that program because we can compile the call to it, even if we don't have the code for it. It's the linker that resolves function calls and function callees, function callers and function callees. So the linker will match up. It'll create the actual executable file. The linker will match up callees from one compilation unit with callers from other compilation units. So if we look at, make sure there's enough space for this. So if we look at the symbol tables, the linker tables for, let me separate these. So here's myprog.o, this is f.o. So myprog.o has an entry for F, but it doesn't know the location of it, whereas f.o has an entry for F. So what the linker does is it looks at these two tables and says, all right, I've got a missing entry here, but I have a defined entry here. So I'm going to combine all of this machine code and update the address of F to be whatever the new address of F is in my linked program. That sort of makes sense? So you can define as many functions as you want in one compilation unit, call as many other functions as you want in another compilation unit, and then the linker step is what resolves those function calls. So this is what allows for separate compilation. It allows for library code reuse. So it's like the early form of like code reuse. So you don't have to rewrite printf or every syscall in every function, every program that you have. You can instead have a library of common calls, and it's the linker that allows you to do that. So you can write programs without actually defining all the functions that you call, and the linker will take the code that somebody else wrote for you and combine it into your program. Does that sort of make sense? All right. So that's how this is how separate compilation works at the low level, like system software level. Okay, so that's separate compilation. Let's see. So I talked about the C runtime a little bit. Okay, I'm seeing how much. Okay, so I think we can get into this. This is maybe a little preview of the rest of the compiler stuff we're going to look at. So when it comes to function calls, in C you just use this syntax to define what a function looks like. But at the architecture level, the processor has no concept of a C function. The processor, so in MIPS, what's the instruction for, say, changing the program counter? What's an instruction that does that? Is this a subtle question? Yeah, what's that? Jump, yeah, jump, right? So all jump does is you have a sequence of instructions, and if you don't call jump, the program counter just gets incremented by one, or one word or whatever, one instruction to the next instruction. But jump will change the program counter so you can branch, go to a different part of the code, right? That's the functionality you have at the architecture level. You don't have a true function call. You don't have local variables or return values. You just have branches. So to actually implement a function call, and we'll look at this in like a month or so, we'll actually implement this. To implement this, the compiler has to do more work to simulate what a C function call can look like on the architecture. And this is standardized. So in order to have your function that you wrote be callable by my program, we need to define some conventions about how that call works. So how are parameters passed, how are return values passed, and then so that way we can set up all this information and then just call jump to go to your function. So for instance, if I say put all the parameters in registers, but you're expecting them to be in memory locations, your function call is not going to work, right? So we have to agree, should we pass parameters in the registers, should we put them in memory? Where's the return value going to be stored? What's going to happen when there's multiple nested function calls? So all this needs to be worked out and agreed on by every programmer who's going to want to call each other's functions. And so this is called the application binary interface. So like you probably heard of application programmer interface. That's the definition of the function calls and their types. That's like the syscalls. That's the syscall API. The ABI is the binary interface when you've got machine code. This is how you can call functions across different compilation units. So we'll look at this in more detail in a month, but I'll just give you a kind of little preview of what this looks like. So remember, the kind of mental model, the low-level mental model we have is we've got an architecture processor that can do arithmetic, it can do logic, it can do branches. And we've got memory. Memory is where we store variables. It's where we store code. So the way the x86-64 ABI works, application binary interface works, that interface for making function calls across in binary and machine code, looks like this. So let's say we have this function defined here. It's got 8 parameters. It's called myfunc. It's got 8 parameters, and it returns a single long, and it has a couple of local variables. Well, the agreement for x86-64 architectures in the Linux platform is that the first 6 parameters are passed via registers. So these are the names of registers in the Intel world. And the rest of the parameters are passed in memory. There's a return address that saves where you jump back to after you finish the call. We'll talk more about the base pointer when we get there. And local variables are also stored in memory. And so this is how this function call, which can't be, doesn't work on x86. If you just call the function call on x86, it's not going to be a C function call. It's not going to have local variables. It's not going to have return values. But this is how the information is passed to and from functions at the actual architectural level, in memory and in registers. So we're going to look at this in much, much more detail when we get to functions. But one of the other tricks here is that this allows for recursion as well. So if you tried to write a recursive function in assembly with just using a branch, it would not work as expected. And I'll show you actually examples of why that breaks down. But the main trick to doing this is using a stack. So every time there's a nested call, the data about that function call is pushed onto a stack. So I think you all learned about stack, right? First in, last out. And this is what allows for recursion to work. And if you ever heard of, say, a stack trace or a stack overflow, this is where this term comes from. Because every time you have a nested function call, data is pushed onto the stack. If you have too many nested function calls, like recursion that you've failed to write the base case, it will exhaust the amount of memory you have for your function stack. A stack trace is just a listing of all the nested functions that have been called so far in the program. All right, but I will get into this in much more detail. There is actually assembly language support for managing recursion and C-like functions. And we're actually going to generate code that follows the function call ABI for x86 64. All right, questions about function calls, source to process, all of the tool chain that takes your source code to an executable program or running program. Questions about this? All right, let's leave it at that. Next time we'll look at some of the foundations of compilers. I did make an assignment today. Oh, I should say this. So there's a new assignment. It's should be very, very simple. It's literally hand copying your very first kind of compiler. It's going to turn infix notation to postfix notation. Just follow the directions here. Let me know if you have any questions. It's really to make sure you have your environment set up on your machine. It's an exercise, not a project. So, yeah, you can start doing that today. All right, everyone, have a good day.